Okay, we're going to get started with Chapter 7. All right, so at this point in chemistry, we are done talking about just elements by themselves. All right, we're now taking the elements, the individual atoms, and now they're going to be brought together and bond together. Because a lot of atoms like to do this, and we'll talk about why. So the first type of bond we're going to talk about here in Chapter 7 is called an ionic bond. So we're going to talk about ions again. All right, we've mentioned them a little bit, and we're going to talk about them in more detail. And then we're going to talk about how they bond together ionically. And then we're going to talk a little bit about bonding with metals. Okay. So in this first part, again, we're just kind of reviewing what an ion is, and then we're going to talk about this concept of valence electrons. Okay, so we've gone through electron configurations by now. You should have a pretty good idea of how to do an electron configuration for any of the elements. We've talked about that pattern that we see across the periodic table. We know that electron configurations describe all of the electrons that are in the atom. But it turns out that we don't need to know about all of the electrons in the atom most of the time. Most of the time, we're only going to be interested in the ones on the very outermost edge. Okay, so that outer shell, the outer energy level that an atom has, those electrons on the very outside are the ones that are going to come in contact with other atoms. So atoms are going to bond with other atoms using those outermost electrons. And that's what we call the valence electrons. So valence electrons are the outermost s and p electrons. So for now, we're going to ignore d and f. So if an atom has d electrons or f electrons, we're going to ignore those for now. We're only going to focus on their outermost s and p electrons. When I say outermost, I mean the energy level that's furthest away from the nucleus, whatever the highest energy level is. Now we know that an s can hold 2 electrons total, and a p could hold 6 electrons total. So the most electrons you could ever have would be 8, right? So when we talk, again, about valence electrons, we're talking about this outer energy level here. We're not going to be concerned with the ones on the inner energy level. So for instance, okay, this right here would be a 3s2 3p4. 3s2 3p4. How do I know that? Because it has 3 energy levels, so I know it has a third energy level here. And it's got 6 electrons, and you always fill the s first. So the first 2 would have been the 3s. And then the next 4 electrons would have all been in the p. So it's a 3s2 3p4. So it has 6 valence electrons, because I lump the s and the p together. And so it's a little bit short of having a full 8 valence electrons. Right? So an octet is the term we're going to use for 8 valence electrons. It's just a term that means 8 of anything, really. But we're going to use it specially here when we talk about valence electrons, because 8 is a magic number. Only the noble gases would have all 8 valence electrons. They would have their octet of valence electrons, which makes them very stable, because that means that their outer energy level is completely full. And so that's what all of the other atoms on the periodic table are striving for. All of the other atoms, every single atom, every single element that is not a noble gas, have atoms trying to form an octet of their own. And to do that, they're either going to have to gain some electrons, or they're going to have to lose some electrons. And in fact, this describes most of chemistry, which is why this is really important. Right? The reason why different elements act the way they do is most of the time because they're trying to gain an octet of valence electrons. And so they're going through whatever chemical reactions, whatever bonding they need to do to get to that point, right? Because that makes them stable. And when they're stable, they don't need to do anything else. right? That's why I put the little happy sign here. Right? Noble gases are already happy. They already have their octet of valence electrons, but nothing else does. So there is a pattern on the periodic table that we can use to determine how many valence electrons there are for any of the atoms. And it's a really simple pattern, right? If you look at the groups on the periodic table, and we're going to skip 3 through 12 for the moment, because 3 through 12 would be right there in the middle of the periodic table. That would be the transition metals, right? The D block. We're going to skip them for a minute because they don't quite fit into this pattern. But if you look at group 1 and 2 and 13 through 18, and we talk about what is their electron configuration, if you're in group 1, that means you're in S1, right? That's all you have. You just have an S1 on your outer energy level. If you're in group 2, however, you have S2. And then if you skip over to group 13 would be the beginning of the P block. So we would have an S2, but now we'd be starting the P, so it would be a S2P1. And so that group 14 would be an S2P2, and group 15 would be an S2P3, and so on and so forth, until we got to group 18, which is the noble gases, and they have a completely filled energy level. So they are an S2P6, right? Everything's completely full. So if we're saying valence electrons is the outermost S and P electrons, then it's pretty clear how many valence electrons are we talking about here. Well, S1 would only have 1. S2 would only have 2. Group 13 is an S2P1, so 2 and 1 make 3. 2 and 2 make 4. We have 5, 6, 7, 8. Now, look at this nice, neat, easy to remember pattern. Group 1 elements on the periodic table have 1 valence electron. Group 2 has 2. 13 is 3, 14 is 4, 15 is 5, all the way to 18 is 8. Okay, nice, simple, easy pattern, right? Group 1 always has 1 valence electron. Group 2 always has 2 valence electrons. 13 is 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7. Now 18 is 8. I do want to point out that helium right here in the upper right hand corner, helium only has 2. Why? Because you have to remember that even though he's in group 18, helium is still only in the first energy level. Well, first energy level doesn't have a P, it only has an S. So helium is a 1s2. Now you might be thinking, well, all the other S2s are over here. Why don't we just put helium right here? Well, it turns out that helium has a full energy level. Just because its energy level doesn't have a P means it can't have 8 valence electrons. It only has 2 valence electrons, but it's still a full energy level. Therefore, it is a noble gas. So therefore, it is most like these, even though it only has 2. So that's one of those little odd things that comes up with valence electrons. The other thing that's a little bit odd, and this is the reason why we left these groups out here, this D block, these transition metals, the transition metals would all be S2s, right? Because they get past the second energy, or the second part of S block. But when we get into this area here, remember these are the D block. This is where they start to fill their D sublevel. Now we said that valence electrons are S and P electrons only. They don't include D. And that's true almost all of the time. Except that there's a few of these here that sometimes do include their D, which makes them just a little bit odd. And so we don't know, we don't have an exact pattern. We could put in how many valence electrons all of these have here, but it wouldn't be a pattern to memorize. So we're not going to worry about those valence electrons, okay? You just need to know that most of them probably have 2. Unless they're one of those exceptions. You remember that when we were doing electron configurations, we said that D4 likes to borrow from the S to become a D5, and D9 likes to borrow from the S to become a D10. Well, if you were to borrow from your 2, you'd be down to 1. So there are a handful of these that would only have one valence electron. Most of them have two. But again, we're not memorizing those, but the rest of these you do need to memorize. And it's a pretty easy pattern to memorize. Now we can graphically show valence electrons too, where you can draw something called an electron dot structure. Instead of having to say something has so many valence electrons, we can actually show it. And it's really simple because we're just going to use dots to represent valence electrons. So let's take neon, for instance. Neon is in group 18 on the periodic table. It's a noble gas. So neon has 8 valence electrons. So if I wanted to draw the electron dot structure for neon, I'm going to start with the symbol Ne, and I'm going to put 8 dots around it. Yeah, it's that simple. Okay? There, I have now shown that neon has 8 valence electrons. Instead of having to say 8, I actually show it with 8 dots. Now, there are not really any rules to where you put the dots, but I will say this. You notice how this is nice and neat with no more than 2 dots on any side? All right, that's how you should draw yours. So you just can't put 8 just anywhere. All right, try to make it neat. They always are no more than 2 on a side, and so we just think of this as an invisible box around this symbol here. So let's do this with aluminum. Now, you need to practice this a little bit, so make sure you have a periodic table out. If you need to, pause, look up aluminum. I want you to figure out how many valence electrons it has, and then I want you to draw that many dots around the symbol Al. Okay, so hopefully you've done that already. You looked up aluminum. Aluminum is in group 13. And if it's in group 13, that means it has 3 valence electrons. So I have to take Al and I have to draw 3 dots around it. Now again, where do I put the 3 dots? You could really put them just about anywhere. We try to put only 1 on a side to begin with, unless we have so many that we have to put 2 on a side. Neon had so many that I couldn't just put 1 on a side because I only have 4 sides to work with. So they needed 2 on a side. But we're going to start with just 1 on a side. So I put 1 here, I put 1 here, I put 1 here. Okay, to make my 3. Could I have put 1 on top instead of the bottom? Sure. Could I do top, bottom, and right instead of left? Yes, it doesn't really matter. You've got 4 sides to work with. Okay, so again, it's not exact rules as to where you put the dots. Just try to make them neat and don't put more than 2 on a side. So otherwise, those are pretty easy. Once you memorize the pattern for valence electrons, and you know where how to draw a dot structure, it's pretty simple. So this would be then the dot structures for those groups that we just talked about memorizing. So here's group 1. We said they all have 1 valence electron, so they would all need just 1 dot when you draw them. Group 2 always has 2 valence electrons, so we put 2 dots around them. We try not to pair them up unless we have to. All right, so you notice we don't have to start pairing up until we get to group 15. Group 15, by the way, is also known as group 5A. So you might see that on some periodic tables where they actually have a Roman numeral 5 above it instead of having the number 15. We call it the group 15 because it's the 15th group over, but it is the 5th group out of the ones that we've been memorizing, right? If we were just talking about the S block and the P block, you notice the D block, they kind of took out of this picture here because, we don't know much about them in terms of the pattern. We don't have to memorize them. So we get to group 15, 5A, and we start to have 5 dots around here. Well, now we have to start pairing up sometimes, right? And then group 16 and group 17, and then this would be group 18, right? And group 18 has 8 valence electrons, except for helium, which only has 2. But what makes them special is they all have a full energy level. Once we understand these valence electrons, then we can move on and talk about things like forming ions and having all of these elements get to a point where they can be like the noble gases.